we do not see a continuous spectrum in atoms or molecules. I don't know if you guys remember, there's a picture in chapter 6 of our textbook where it has a guy running up steps. And that's to indicate that the atomic levels or the atomic energy levels in an atom are discrete. Okay, they happen in a stepwise fashion, not a continuous fashion. To further illustrate this point, we made you do a hydrogen spectrum lab towards the end of Chemistry 121, where you went in the balance room, you looked through a spectroscope, and you saw a bunch of different lines. Okay? You didn't see a continuous spectrum through there, you just saw lines. Right? So those lines, when you look through that spectroscope, have different colors on them. So you have to kind of think, okay, what is that telling me? If a line is a different color, if I saw a line in that spectrum and one's purple and the other one's red and the other one's orange, that tells me that they have different energies. And we can use those values of energies to start determining what's happening and where the electrons are residing in a particular atom or a particular molecule. So the point in putting this slide up right here is to show that each of the wavelengths of visible light have a different energy. And we can use that energy to come up with some type of electronic information or an electronic structure in a particular atom, in a particular molecule, or in a complex ion. So keep all of this electromagnetic radiation stuff in the back of your mind, and we're going to use different parts of this electromagnetic spectrum depending on what our outcome or our goal is. If we want to excite core electrons that are really close to the nucleus to a really high level, we're going to need some potent radiation to do that. You're going to use an instrument called an X-ray fluorescence analyzer to use X-rays to do that. In the transition metal lab, we don't need radiation that potent to analyze the colors of transition metal complexes. So we're going to use a UV vis spectrometer to analyze those. So here's our electromagnetic spectrum. It kind of gives us a background of the color. So the next question we need to ask ourselves is, how does our eye detect color? And more importantly, how is that color that we see with our eye related to an absorbance? Because our UV vis spectrometer is going to measure absorbance. So some of you may remember back from art class, kind of back in middle school, where they give us this little color wheel right here. So I'm going to give a rough sketch of that color wheel, and we can put in letters here for each of the colors that we're going to analyze. The question that was posed is, how does our eye detect color? So what we can say about this, and what our generic definition will say, is that if absorbance occurs in one region of the color wheel, the material appears with the opposite, which we refer to as complementary color. And hopefully you've kind of seen this before. So what we can say is that if our particular material that we're analyzing, or our complex ion, if we have an absorption in the violet region of the spectrum, it's going to be yellow to the eye. Because if we look here in the color wheel, if our absorption is violet, the color to our eye is going to be the complement or the opposite in the color wheel, and it's going to be yellow. If a particular material absorbs green, it's going to be red to the eye. And we look back at the color wheel we've drawn here, so if we absorb green, we're going to see red to our eye. So you can use this color wheel. If you notice in the labs, there should be a bunch of color wheels posted on the windows in there. You're going to use that and use the wavelengths of the visible, visible light to try to solve some of your problems and analyze things. Yep.
This is really an important question or not, but is there supposed to be an eye in that wheel, or is that not?
So one of the things is the question was, is there supposed to be an eye for indigo in the wheel? And it's kind of like every time we like symmetry, right? So the little pie pieces in Trivial Pursuit, there aren't 7, there's 6. So indigo kind of gets the shaft here for the, in the color wheel. So we just kind of list that, but indigo is kind of in between blue and green, so you kind of can approximate that. Okay? So this is typically what we teach younger students in an art type of a class. Okay? What we typically don't say is what happens if a particular complex absorbs in more than one place in the visible spectrum. So we also need to say that if absorbance occurs in multiple regions of the color wheel, the material takes on a color in the middle of the colors not absorbed. Or it's going to be the complement of those in the middle. For example, if, for instance, and I'll throw the color wheel back out here. So if, for instance, we absorb violet, blue, and green, what would our color look like? So we have to look at the color wheel, and we're going to absorb all 3 of these over here. That means the color to our eye is going to be the middle color of those not absorbed, or in this case, orange. So if I absorb violet, blue, and green photons, it's going to be orange to our eye. If, on the other hand, we absorb violet and red, we're going to observe to our eye a yellow-green color. So using the color wheel, it will allow us to look at a particular color we observe to our eye, and then what the absorbance is going to be, and what wavelengths of visible photons that particular material, which has a color, will look like to our eye. Okay?